Hello students, welcome to the video on solar cells. So in the previous videos we have discussed about what is an PN junction diode, and we have also seen what is an optoelectronic device. So in optoelectronic device we have three applications, that is one is photo detection, another one is photo conversion, and then light emitting diodes, that is photo emissions. So here in this video we will be discussing about solar cell. So solar cell is nothing but a photodiode which will convert the light energy to the electrical energy. So here we will discuss how a solar cell operates and what are the requirements for a solar cell. So we know that when light shines on the solar cell, there is a large drift current due to the minority carriers. That is, when I reverse bias a PN junction diode, so there will be a current due to the minority carrier, and that results in a current called as reverse saturation current. This reverse saturation current is very small in a normal PN junction diode, and it is of the range of microamperes. But when I make a light to fall on the device, that is when I make the solar light or solar energy to fall on the device, then in another type of current is used or generated, which is called as the light generated current IL or IOP, which is nothing but optically generated current. So this current will be flowing through the device, and the voltage generated due to the light will bias the PN junction diode in the forward bias mode. So normally in an operation of a photodiode, the solar cell will come into the fourth quadrant. So the diffusion current flows as it is in the opposite to the direction of the light generated current, and the total current is given as I naught I total is equal to I minus IL, where I is the electrically generated current and IL is the light generated current. So here when we go for the design consideration of the PN junction for a solar cell, we have three important factors to be considered. The first one is nothing but the surface area, the second one is doping, and the third one is junction depth. So what is meant by surface area? So when the light energy falls on the device, we know that we want to get the maximum output from the light energy. So the current generated will be depending on the illuminated area. So to get more output current, so that the area should be more, but we have only the IOP of the range of 10 to 100 milliamps for a junction with an area of about 1 centimeter square. So in this case, to utilize the maximum amount of available optical energy, that is to get maximum optical energy to be converted to the electrical form, a large area of the junction should be located near the surface of the device. So for this case, we will be forming the planar junction either by the diffusion or ion implantation process, and also the surface of the device should be coated with appropriate materials to reduce the reflection and also to reduce the surface recombination. So the first point is our surface area. So the surface area should be wide, and it should be such that there will be maximum electrical energy generated or the electron hole pair formed. So the next one is doping. The third one is junction depth. So that there should be a proper match between the electron diffusion length Ln, the thickness of the p region, and the mean optical penetration depth 1 by A. So what is optical penetration depth? So the amount of the how much amount of length the optical energy is, or the light energy or the photons are able to penetrate into the device is called as 1 by A. So that should be comparable, and it should be more than the electron diffusion length Ln, so that more of the charge, the optical energy when it falls on the device is converted to the EHB. And also the thickness of the P region plays a very important role in the device fabrication. So in this slide, we can see the some of these solar cell arrays which is arranged or which is used in the International Space Station. And the second diagram is the solar plant which is placed in Italy. Now, when we have a large contact potential V naught to obtain a large photovoltage, therefore heavy in the doping will be used, but heavy doping will results in some defects, that is long lifetime are desirable, and these are reduced by doping too heavily. Also, the series resistance of the device will be very small. Power is not lost due to heat ohmic loss in the device itself. If the area is large, the resistance of the PTA body of the device can be made small. However, contact to the thin end region requires a special design. So the current must flow along the thin end region of the contact, resulting in large series resistance. To prevent this effect, the contact can be distributed over the end surface by providing small contact fingers. This narrow contact serves to reduce the series resistance without interfering appreciably with the incoming light. So in this diagram, we can see there that this is the device fabricated. The P region depth also plays an important role, and this is the D. So our device should be such that the penetration depth width of this device of this solar light energy should be such that it should cross the transition region. And here these are the finger like contacts are which is used to reduce the series resistance of the device. So in the next case, we will be seeing what are the characteristics of a solar cell. So the solar cell characteristics, we have four important parameters. One is short circuit current, open circuit voltage, fill factor, and efficiency. So what is meant by short circuit current? So when the device is reverse biased and the amount of light energy which is falling on the device when the amount of light energy falling on the device will result in a current, and that current is called as the ISC. So normally ISC should be large. And what is open circuit voltage? So the voltage which is developed across the device when light energy is falling on the device is called as the open circuit voltage. So the fill factor is nothing but the ratio of the fill factor is nothing but the ratio of VMIM by VOC into IOC. So here what is VM? So here the short circuit current is measured in terms of milliamps per centimeter square. So the voltage is given by the equation VOC is equal to KT by Q into ln of IL by I naught plus 1. So maximum VOC for the silicon solar cell is 0.85. Now, what is fill factor? Fill factor is VMIM by VOC into ISC. So this is open circuit voltage and the short circuit current are the should will decide the fill factor of the solar cell. So the fill factor will be normally around 0.8. Fill factor, it represents the losses in the PV cell. The efficiency of the solar cell is also depending upon the band gap. So the short circuit current decreases with the increase in the band gap, and open circuit increases with the increase in the band gap. So there is an optimum band gap for maximum efficiency. The maximum solar cell efficiency is about 31% and is obtained by the optimum band gap of 1.45 electron volt. The efficiency calculated at 1.5 am and for a single junction cell. So in case of a single junction device, the efficiency of the solar cell, the ratio of the power produced and the incident light power are all limited. Photons with the energy below the band gap of the material produces only heat. Excess energy above that needed to generate the electron hole pair also produces the heat. So in this case, we go for a multi-junction device in which two or more solar cells are stacked on top of each other and can exploit the different portion of the solar spectrum. For example, a 4-junction device with a band gap of 1.8, 1.4, 1.0 and 0.7 electron volts results in a theoretical efficiency of more than 52%. The multi-junction approach, however, presents significant challenges in both the material preparation and the device design. So to reduce the loss or to improve the efficiency of the device, we go for an we have multiple layers of the device, that is called as heterojunction cells. We using gallium arsenide and aluminum gallium arsenide, etc. So here in this we can use a concentrators to make the light energy fall on the device, and also a well-made silicon crystal can have up to 25%